So here's another integral that we're faced with here, and as always, when you have an antiderivative that you're trying to determine, your first hope is that one of your formulas works, and in this case you don't have a formula that's going to work right away, so that's not really an option. You can try to do a u substitution. If you try to let u equal the sine function here, you're going to pick up a cosine of x when you compute du dx, and there's not another cosine sitting anywhere for you to cancel with, so it doesn't really seem like that's going to work. Whenever you have powers on sines and cosines, what you're going to more than likely have to do in order to evaluate the integral is use some combination of these trig identities over here. Now, in this case, whenever we have a power that's even and no power that's odd, we're actually going to go with our half-angle identities as opposed to the Pythagorean identity. So in this case, we have a sine squared of x. We can replace sine squared of x with this expression, and if you make that substitution, you will definitely be looking at something that you're going to be able to handle. So you're going to put 1/2 times the quantity 1 minus cosine of 2x in place of sine squared. And we're going to be able to do this integral now. We're going to be able to distribute this 1/2 in, break it up into two different integrals, and we're going to be looking at two integrals that we can actually manage with. What would have made this a little more complex is if there would have been like a sine to the fourth. You would have had to break that up into sine squared times sine squared, apply this twice, you would have had some foiling to do, and you would have had a much longer process to go through, but you still would have been able to evaluate the integral by applying this formula to it. Same thing can be said if this was sine squared times cosine squared. You can replace the cosine squared with this, sine squared with this. You could FOIL these together and make one more substitution with an identity a little bit later on, and be able to evaluate the integral that way. In this case, we're a little bit luckier because we have an integral that is going to turn out a little bit more quickly than either of those situations I just described there. So I'm distributing my 1/2 in to the 1. And I'm also breaking this up into two different integrals. So the integral on the left here, right, with the 1/2 distributed into the 1, that's an easy integral. Nothing weird about that. Now the integral here we have to be a little more careful with. We do still have this inner function sitting right here, so we are going to want to let u equal 2x and make sure we go through the substitution steps in order to pick up the appropriate constant that's going to sneak into the mix there. But we're definitely going to be able to evaluate both of these integrals. I'll do the rest of the substitution steps here. So du dx would then be 2, and then du over 2 is what we're going to be able to put in place of the dx. The integral on the left you can do right away. The integral on the left, the integral of 1/2 with respect to x, is going to be 1/2 x. I could put a plus c there, but I'm going to subtract the antiderivative of this. I'm just going to put 1 plus c at the end of this line. So then I'm going to have minus 1/2 times the integral of cosine of u, right? So I've put I've replaced my 2x with a u, and then in place of my dx, I'm going to put du over 2. And so you see what happens is you pick up this extra factor of 2 in the denominator there. So if we go ahead and bring this factor of 2 out to join this factor of 2, that's going to leave us with a coefficient of 1/4, and then the antiderivative of cosine is sine, and then it's going to be sine of u. I could write sine of u here. I'm going to back substitute at the same time. I'm going to write sine of, not 2u, but 2x, my fault, sine of 2x. And this is where I want my plus c. So there we go. We applied one of the half-angle identities, did the integral, not too bad. Could have been a little worse if we would have had a higher power that was even. We would have had to apply these several times and then do some foiling before being able to do the antiderivatives. But in this case, apply this, break it up, little minor u substitution, you've got your result.